Hey everyone, welcome back to Chem's Story. Today we're diving into one of the fundamental reactions in organic chemistry, E2 elimination. We'll break down exactly what it is, see how it works, and explore the key factors that affect its rate. Let's start with the basics. Elimination reactions involve removing two substituents from adjacent carbons, creating a new pi bond. Simply put, a double bond forms when two groups leave the molecule. We can divide elimination reactions into three main types, E2, E1, and E1CB. Each has a unique mechanism, which we'll explore later. But first, let's get a quick overview of how they differ. E2, bimolecular elimination, is a single-step reaction. Here, both the base and substrate participate in the rate-determining step. There are no intermediates involved. Instead, the leaving group and a proton are removed simultaneously, forming the double bond in just one step. E1, or unimolecular elimination, happens in two distinct steps. First, the leaving group departs, forming a carbocation intermediate. Then, a base removes a proton from a neighboring carbon, resulting in double bond formation. Because there's a carbocation intermediate, rearrangements can occur. E1CB, or elimination via a conjugate base, is also a two-step process, but here, the proton leaves first. This forms a carbon-ion intermediate. Then, the leaving group departs, allowing the double bond to form. You'll often encounter this mechanism when the proton being removed is especially acidic, like in beta-carbonyl compounds. We'll dive deeper into each mechanism in future lessons, but for now, remember this simple distinction. E2 happens in one step, while E1 and E1CB involve intermediates. Alright, now let's zoom in on the E2 reaction and explore the key factors that control its rate and determine its outcomes. E2, also called bimolecular elimination, follows a concerted mechanism. That means bond breaking and bond making occur simultaneously, all in a single step. The base removes a proton at the exact same moment the leaving group departs, creating a double bond in one smooth motion. Because all bond changes happen together in one transition state, there's no opportunity for intermediates to form. In E2 reactions, the sigma bonds that break are stronger than the pi bonds that form. Because of this energy difference, E2 reactions are typically endothermic. And since both the substrate and the base influence the reaction rate, E2 follows a second-order rate law. Rate equals K times substrate concentration times base concentration. In other words, the reaction is first-order with respect to each reactant. Now let's go through a clear example of the E2 mechanism. Here, a strong base, like hydroxide, removes a beta hydrogen from the substrate. For this to happen smoothly, the beta hydrogen and the leaving group must be positioned antiperiplanar. That means directly opposite each other. This alignment is crucial because it allows ideal orbital overlap in the transition state. As the base takes away the proton, electrons from the CH bond shift to form a new pi bond between the two carbons. At the exact same moment, the leaving group, bromide in this example, detaches from the adjacent carbon. Because this process is concerted, bond breaking and bond forming happen simultaneously, giving us the alkene product in a single step. Now let's look at the energy profile for an E2 reaction. The y-axis shows energy, and the x-axis shows reaction progress. Starting from the reactants, energy rises until reaching the highest point, the transition state. This peak represents the most unstable stage, and the energy required to reach it is called the activation energy, or EA. After the transition state, energy decreases as products form. Since stronger sigma bonds break and weaker pi bonds form, E2 reactions are typically endothermic. With the mechanism and energy profile clear, let's move on to regioselectivity in E2 reactions. Here's where things get really interesting. Elimination reactions, especially those involving alkyl halides, tend to be more complex than substitutions. Why? Because elimination can occur in multiple ways, leading to several possible products. That's what makes them fascinating, and, honestly, a little tricky to predict. The key point here is simple. If the molecule has more than one beta hydrogen, the reaction doesn't produce just one alkene. Instead, you get a mixture of different alkenes. And that's exactly where regioselectivity becomes important. So, how do we predict which alkene will dominate? That's where Zaitsev's rule, also called Zaitsev's rule, comes into play. According to this rule, the more substituted alkene typically forms as the major product. Why? Because more substituted alkenes are thermodynamically more stable. Additionally, the transition state leading to the more substituted alkene usually has a lower energy barrier. This means the reaction naturally favors this pathway. It's simply faster. In short, although E2 reactions can produce multiple alkenes, the more substituted one usually dominates, thanks to its greater stability and a more favorable reaction pathway. Let's break this down using 2-chlorobutane as an example. Here, the base has two possible pathways, forming two different alkenes. In route A, the base removes a proton from the terminal beta carbon, giving 1-butene. This alkene is less substituted, and therefore less stable, so it's the minor product, around 20%. In route B, the base removes a proton from the more substituted beta carbon, producing 2-butene. Because it's more substituted and more stable, it's the major product, around 80%. One more quick note, 2-butene exists as cis and trans isomers, and the trans isomer usually dominates due to less steric hindrance and greater stability. Now, another quick example, 2-chloro-2,3-dimethylbutane. Again, there are two possible pathways. In route A, the base removes a proton from the terminal beta carbon, giving 2,3-dimethyl-1-butene. It's less substituted, less stable, and forms only about 21% of the mixture. In route B, the base takes a proton from the more substituted beta carbon, forming 2,3-dimethyl-2-butene. Because it's more substituted and more stable, it's the major product, around 79%. This outcome matches Zaitsev's rule. The more substituted alkene usually dominates. So why does the reaction prefer the more substituted alkene? To explain this clearly, let's look at the transition state using the Hammond postulate. This postulate says the transition state resembles the products, especially in endothermic reactions like E2. Because the transition state resembles the products, a more stable alkene leads to a lower energy transition state. More substituted alkenes are stabilized by hyperconjugation and inductive effects, lowering activation energy. If you check the energy diagram, you'll see the path leading to the Zaitsev product. The more substituted alkene has the lowest activation barrier. That's why it's usually the major product. So far, we've focused on Zaitsev's rule, where E2 reactions favor the more substituted, stable alkene. But under some conditions, the opposite happens. The reaction can favor a less substituted alkene instead. This is called anti-Zaitsev, or Hofmann elimination. Hofmann elimination occurs mainly due to steric hindrance, especially with bulky bases. When a base is too bulky to easily reach the more hindered beta hydrogen, it takes the proton from the less hindered carbon. The result? The less substituted alkene becomes the major product. Now, let's look at Hofmann elimination, an example of anti-Zaitsev elimination. Here's the key point. Because of steric hindrance from the bulky leaving group, the base struggles to reach the more substituted, crowded beta hydrogen. Instead, it takes the less hindered proton, giving the less substituted alkene as the major product. Unlike typical E2 reactions that follow Zaitsev's rule, Hofmann elimination strongly favors the anti-Zaitsev product. For example, when a quaternary ammonium hydroxide compound A undergoes elimination, the Zaitsev product forms in just about 2%. Meanwhile, the Hofmann product dominates at 98%, mainly due to steric hindrance. Another example is compound B, a cyclohexylamine derivative. It follows the same process, forming a quaternary ammonium salt, then eliminating upon heating. Again, the less substituted alkene comes out as the major product, clearly showing anti-Zaitsev selectivity. E2 reactions rely on a strong base to remove a beta hydrogen and drive elimination. But here's the key. The size of the base plays a big role in which product forms. Small bases can easily approach the substrate. In primary alkyl halides, they might even lead to substitution instead of elimination. Bulky bases, on the other hand, create steric hindrance. They have trouble reaching the more substituted beta hydrogen. As a result, they tend to favor anti-Zaitsev elimination, giving the less substituted alkene. So depending on the size of the base, the reaction may follow Zaitsev's rule or shift toward the anti-Zaitsev pathway. When small, strong bases are used, E2 reactions usually follow Zaitsev's rule. This leads to the more substituted and more stable alkene as the major product. Common examples of small bases include sodium hydroxide, sodium methoxide, and sodium amide. Bulky bases tend to favor anti-Zaitsev elimination. Why? Because they struggle to reach the more crowded beta hydrogen. Examples of bulky bases include potassium tert butoxide, lithium disopropylamide, LDA, and the bicyclic bases DBU and DBN. Let's take a closer look at an example. When a tertiary alkyl halide undergoes elimination, it can produce two possible alkenes, compound A, the less substituted product, and compound B, the more substituted product. The type of base used plays a key role in determining which product is favored. With a small, strong base like hydroxide, the reaction follows Zaitsev's rule. That means compound B, the more substituted alkene, becomes the major product. In this case, compound B forms in 79% yield. Compound A, the less substituted alkene, makes up only 21% of the mixture. But when a bulky base like potassium tert butoxide is used, the result changes. Steric hindrance prevents the base from removing the more substituted beta hydrogen. Instead, it removes the proton from the less hindered position. This leads to anti-Zaitsev elimination. Now, compound A becomes the major product, forming in 75% yield, while compound B drops to 25%. That's why the choice of base is so important. It lets you control the reaction and predict the outcome. Now that we've seen how the base affects elimination, let's move on to another important factor, the substrate itself, and how it influences E2 reactions. The structure of the alkyl halide has a major impact on how fast E2 happens. Since E2 is a concerted reaction, the stability of the transition state controls the speed. In general, more substituted alkyl halides react faster. Why? Because alkyl groups help stabilize the pi bond forming in the transition state through hyperconjugation and electron donating effects. This added stability lowers the activation energy and speeds up the reaction. The degree of substitution also affects the reaction pathway. Highly substituted substrates tend to favor elimination because substitution becomes harder due to steric hindrance. On the flip side, primary alkyl halides often go through substitution unless a bulky base is used to push elimination. So, by understanding substitution patterns, we can better predict how E2 reactions will behave. Solvent choice also matters in E2 reactions. It affects how strong and available the base is. Since E2 needs a strong base to remove the beta hydrogen, the solvent should support, not weaken the base. Polar A product solvents are ideal. They dissolve ionic compounds but don't hydrogen bond with the base. This keeps the base free and reactive, helping the reaction move faster. Common examples include acetone, DMSO, acetonitrile, and THF. These solvents work well with strong bases like sodium ethoxide and potassium tert butoxide, keeping them active during the reaction. That's all for today's lesson. E2 reactions are a core concept in organic chemistry, and understanding them gives you a strong foundation for what's coming next. In the next lesson, we'll focus on stereochemistry and take a closer look at anti-periplanar geometry in E2 mechanisms. Thanks for watching, and I'll see you next time.